All right, so we are going to be moving into chapter 5 now of the David Lay Linear Algebra book. This chapter is going to focus more on some topics that, especially a lot of y'all who may be doing some kind of engineering, these next two chapters are where you'll start seeing what's going to show up in some of y'all's classes down the line. We're going to use some stuff we've learned, and we're going to learn some new stuff and start kind of getting to more of the application-based and more of the STEM engineering-based parts of this class. So before we get into some of the applications, something we need to talk about is the idea of eigenvectors and eigenvalues. So this is kind of our next combo section. These are actually two separate sections in the textbook, but they so closely align with each other, I thought it would be best to teach them at the exact same time. So that's kind of what we're going to do here. What I want to do first is I want to spend a little bit of time defining what an eigenvalue is first, and then we will define what an eigenvector is on the next slide. After we define them, then we'll talk about how you actually find them yourself. So I've done and taught eigenvalues many different ways, and this seems to be the way that sticks the best with majority of students. And that's instead of giving you some ugly definition to start off, let me show you an example instead. So let's assume that we have a matrix A that's 3, -2, 1, 0, and then here's two column vectors that I've specifically made up. Let's let vector u be -1, 1, and let's let vector v be the vector 2, 1. The images of u and v under multiplication by A are shown in the following figure. All right, so right here below the figure, I kind of did the arithmetic and did the algebra already. I took matrix A and I multiplied it by vector u that I defined, and I multiplied the same matrix A by vector v. And what you'll notice is that we got results. I got the vector -5, -1 over here, and I got the vector 4, 2 over here. And you can double check my arithmetic if you need to. Using that and the illustration above, let me show you what I noticed happened. So if you were to, oh, wow, sorry, I hit a wrong button and jumped. All right, so there we go. As you can see in this diagram, and we'll use the left-hand side, you have your vector u that's defined here, which that would just be the vector -1, 1, left 1, up 1. When I multiplied it by A, I got a different vector that went in a different direction. That's nothing of the ordinary. That happens all the time. When you multiply a vector by a matrix, it changes to another vector in a different direction. What should catch your eye here is what happens when we do A times V. If you were to plot vector V, you see you're right here at the point 2, 1 in quadrant 1. And when you multiply it by this specific matrix A, you actually get a vector that is going in the same direction as the original. You may be thinking, okay, so what are you trying to harp on here? Well, I'm harping on that multiplying a matrix by a vector can sometimes be equivalent to multiplying it by a scalar as well. And that's the idea we're going to get into. So kind of putting it in a little bit better wordage here below. Notice that AV is just equivalent to 2 times V. So that matrix A is actually equivalent to a constant. Now, we know that matrices and constants are not the same thing. They have different characteristics. But it's interesting that that can be true for certain types. What A is doing is it's just stretching the original vector. And while that may seem, okay, that's kind of neat, maybe, this actually opens up a whole new branch of linear algebra where when this particular phenomenon happens, what does this tell us and where's it going to lead us in this class? That's what I hope to get from y'all over the next couple of videos as we go through chapter 5. So this section, or these sections we're about to study, we're going to study things like AX equals 2x. So I just substitute my values in, where special vectors are transformed by A into scalar multiples of themselves. All right. Now, will it always be a 2? No. It can be any scalar that makes this statement true, but as that value changes, we'll call it something, and then I'd go from there and define some other things. So that's what we're going to study for the next, I think it's 3 or 4 videos in chapter 5. This is what we're going to be talking about. So let's put some words to this idea. All right. So an eigenvector, which is technically the first thing the book defines, an eigenvector of an n by n matrix A is a non-zero vector x such that A times X equals lambda times X for some scalar lambda. So if there exists, and once again, the key word there is non-zero. You can't use the zero vector here. If you have a non-zero vector X, such that if you multiply it by a matrix A, and you can find a scalar lambda that you can also multiply it by, this gives you an equality that you see. So while X is called the eigenvector of this statement, that lambda is something you're going to have to also be able to find. What lambda makes this statement true as well? Well, that scalar lambda is what we call the eigenvalue of a matrix A. All right. So a eigenvalue of A is true if there is a non-trivial solution X of this particular matrix equation. All right. So for this equation, AX equals lambda X, lambda is going to be called the eigenvalue and X is called the eigenvector in this particular equation. We're going to get into how to find these by yourself in just a second, but the first thing I want to show you is how do you verify something is an eigenvector, and then can you figure out what its eigenvalue is from there. So let me show you an example. Let's assume that we have a 2x2 matrix A, 1, 6, 5, 2. And I've made two particular vectors here to show you this idea. I'm going to let vector U be 6, negative 5, and I'm going to let vector V be 3, negative 2. Two questions for you. Number one, figure out whether A or U and V are eigenvectors of A. So that'll be part one of each question. If they are an eigenvector of A, then you need to be able to tell me what eigenvalue corresponds to that eigenvector. So here's how we check this. What you want to do is you want to begin, and you're trying to answer the question, if you multiply A times U, does this equal a scalar multiple of the original vector U? So what I'm going to do is I'm going to take my matrix A, and I'm going to multiply it by vector U. And so I'm going to use the row column rule to do this. A 2x2 matrix multiplied by a 2x1 should give you a 2x1 vector. I'm going to take the first row of matrix A and multiply it by the column. So 1, 6 times 6, negative 5 would be 6 minus 30, which is negative 24. And then if I take the row 5, 2 and multiply it by 6, negative 5, you'll get 30 minus 10, which is 20. And what you're looking for here is, are these two vectors now multiples of each other? And that will answer your first question. Well, yes, you can get from vector U to the vector lambda U by multiplying by a particular lambda. So the first answer to your question is yes, U is an eigenvector of A. And for your lambda value, just figuring out what you're multiplying by, it looks like you're multiplying by negative 4. So we can define our lambda in this case as negative 4 that corresponds to this particular eigenvector. Now, keep in mind, not every vector is an eigenvector just because we claim something is. Let me show you what will happen if it doesn't work. So on the next one, we are trying to verify if I multiply the same matrix A times vector V, will it create a multiple of itself? Well, if I take matrix A again, and this time I'll multiply it by the vector 3, negative 2. So doing my same steps, if I take the first row of matrix A and multiply it by the column, that would be 3 minus 12, which is negative 9. And if I take the row 5, 2 and multiply by it, that would be 15 minus 4, which is 11. If you look, asking yourself, can I multiply a certain number by the original vector and get the vector that I found? Well, the answer is no. 3 times negative 3 would get you negative 9, but unfortunately, negative 2 times negative 3 is not 11. So this does not work. So your answer to this one is simply no. V is just not an eigenvector of this matrix. And if it's not an eigenvector, there is no eigenvalue to correspond to this. All right, so now that we know how to verify if an eigenvector is there and what the eigenvalue is, the question now becomes well, how do you do it yourself without me giving you part of the answer? So how do we find the eigenvalues and eigenvectors of a square matrix A? So first thing you will have to do is you will have to find your eigenvalue first. The scalar lambda is an eigenvalue of an n by n matrix A if and only if lambda satisfies the following equation. So we are going to end up solving the following. We're going to take the determinant of a minus lambda I, and we're going to set that equal to 0. And whatever lambda you can find to satisfy this, we call that an eigenvalue. Now, this actual equation that you're going to be solving is a specific equation that this book calls the characteristic equation. So this is how we will find eigenvalues. Now, once you find an eigenvalue, you need to then resolve, and this is where the actual linear algebra comes in. You're going to have to solve the homogeneous matrix equation of a minus lambda I times vector x equals the 0 vector. You've got to figure out what vector x makes this statement true. Whatever this vector x is, this will be your eigenvector. All right. Now, there could be more than one eigenvector for an eigenvalue. That's not always the case, but usually it does happen. So what I'm going to state now is that the set of all solutions of a minus lambda I x equals 0 is called the eigenspace of A corresponding to an eigenvalue lambda. So if somebody asks you for the eigenspace of an equation, it wants every single eigenvector that exists. Now, the good news is that we know how to write infinitely many solutions as vectors. We're going to bring that back up here in a minute when we work our first few problems. All right, so now that we've gone over the equations here, let's do some examples and let me show you how you'll do this yourself. So on the first example, I guess example 2 for this video, if I give you a 2 by 2 matrix A, 8, 2, 3, 3, I want you to find 3 things for me. I want you to write out the characteristic equation, use that to help you find the eigenvalues of the matrix, and then once you find the eigenvalues, we will then find the eigenvectors of each eigenvalue. So the characteristic equation part, that's the formula we just went over. We have to take the determinant of a minus lambda I, and we've got to figure out where that equals 0. So first thing we got to talk about is, well, what the heck is a minus lambda I? Well, let's actually substitute what this is. A is just the matrix that's given, minus lambda, which remember, lambda is just a scalar, so it just sits out there in the front. And then we know I to be the identity matrix. Since we're working with a 2 by 2 matrix, we define the identity matrix as 1, 0, 0, 1. If you were to multiply the lambda through, because you're allowed to do that because it's a scalar, you will end up subtracting the matrix lambda 0, 0, lambda. And when I do that, we end up with 8 minus lambda, 2, 3, 3 minus lambda, because you're allowed to subtract matrices that are of the same dimensions. Now, this will be the only time I actually work this all the way out to show you how it works. What we can notice now is that essentially, when you are subtracting lambda I from a matrix, all that entails is you subtracting lambda from the main diagonal entries of matrix A. So going forward, I will always jump straight to a minus lambda I, because there's not really much you have to do there. That's true for any square matrix. So now going back to my problem, I need to find the determinant of this. So to find the determinant of a minus lambda I, we know how to find the determinant of a 2 by 2. this would be 8 minus lambda times 3 minus lambda, and then I'll subtract 3 times 2, which is 6, and we're going to end up setting this equal to 0 in just a minute. If I were to work this out, you would get 24 minus 8 lambda minus 3 lambda plus lambda squared minus 6 is 0, just by filling out your polynomials. If I were to restructure this in standard form, I would write this as lambda squared, combine your lambdas to get minus 11 lambda, and then combine your constants to get positive 18 is equal to 0. We're going to factor this. So if you were to factor this quadratic, you should get lambda minus 9 times lambda minus 2 equals 0. And then if you set both of these equal to 0 here, you will notice that you end up with two different eigenvalues. Lambda equals 9 and lambda equals 2. And so you have now answered technically question 1 and question 2 at the same time. The characteristic equation is this part right here before you factor. And then your lambdas is what your eigenvalues are in this problem. Now, for part 3, for every eigenvalue that you find, you have to find the eigenvectors. So the formula for eigenvectors is A minus lambda I times vector x needs to equal the 0 vector. So we have to solve this for each lambda you just found. And I'm going to do these in numerical order just for simplicity. I'm going to begin with lambda equals 2. So for lambda equals 2, what you're being asked to do is you're being asked to take 2 and plug it into your A minus lambda I. So now I'm going to go back up here to the top right, and I'm going to let those lambdas be 2's and simplify them. So when I plug that in, you should get 6, 2, 3, 1. And since I'm trying to solve the homogeneous equation to create the augmented matrix, I need to add the 0 vector on the end. What you will notice here, and this happens a lot, these two rows are multiples of each other. Row 1 is double of row 2. So what that means is that the most bottom row here must go to all zeros. Okay? On top of that, I also notice that the top row can now be scaled. So I'm going to take row 1 and I'm going to multiply it by a 6 to get a 1 in the upper left position. So that would be 1. A 6 of 2 is a third, and then 0. These are usually pretty simple to reduce. What this tells us, this first row, is that x1 plus a third of x2 must be 0. And then since there is no pivot position in the next column, x2 must be free. Solving for your basic variable, we can say that x1 is equal to negative 1/3 of x2, with x2 being a free variable. And then we know how to write this solution. This means that vector x would equal x2, which is the free variable, and the coefficients you would get here are negative 1/3. Oops, sorry, I keep hitting the button. Negative 1/3, 1. That is your eigenvectors. Every single x2 value except, remember, x2 cannot be 0 because you cannot have the 0 vector. Any x2 that you pick other than 0, that will be an eigenvector of lambda equals 2. Now, you got to do this again because every lambda has a different different types of eigenvectors. So down here below, I'm now going to move to lambda equals 9. That's the next one we found. Going back to my A minus lambda I matrix, we're going to let the lambda be 9 this time. So 8 minus 9 is negative 1, then 2, 3, and 3 minus 9 is negative 6. And I'm going to stick the 0 on the end. Once again, row 1 and row 2 are multiples of each other. you can multiply row 1 by -3 to get row 2. So thus, once again, your most bottom row goes to all zeros. And to make the top row a little bit easier to work with, I'm just going to take the negative of R1 to make that first pivot position, and actually only pivot position, be a 1. So that would give me 1, -2, 0. This tells me that x1 minus 2x2 needs to be 0, with x2 being a free variable. And if I solve for the basic variable, x1 needs to equal 2x2 with x2 being free. Writing that in parametric vector form, which we've been doing since chapter 2, essentially, this is going to end up being x2 multiplied by the vector, and you should get 2, 1 as your elements. So once again, plugging in any x2 other than 0 into this equation will generate an eigenvector of lambda equals 9. And so that is how you find your eigenvalues and eigenvectors of a square matrix. You can already see, just on even on a 2x2, it is a little bit more time consuming to do this. And that's why these next 2 chapters are important to get down the ideas as we're learning. All right. On the next one, what I want to do next is practice just finding eigenvalues of bigger square matrices. So I'm going to take the eigenvector part off for a second. Let's just focus on eigenvalues. So here's a 3x3 matrix. What are the eigenvalues of this matrix? Well, once again, we need to take the determinant of A minus lambda I and set that equal to 0. So what that means, remember, A minus lambda I, you're going to take the entries on the main diagonal and you're just going to subtract lambda from them. So this is asking us to find the determinant of 1 minus lambda, 1, 0, 6. The middle one will become 0 minus lambda, which is just negative lambda, 5, and then 0, 0, 2 minus lambda. Since we're finding the determinant of a 3x3 matrix, you can pick any row or column to do your cofactor expansion. So I'm looking for a row or a column with more zeros, so I'm actually going to pick row 3 to do this. Since we're doing an odd row, we start positive and you alternate throughout from there. So this would technically be positive 0 times, we don't care, because the matrix that's going to come from the submatrix, sorry, I forgot the word. The submatrix will not matter because it's going to go to 0. Then you go minus 0 times, once again, we don't care because its submatrix is irrelevant. And then you're back to plus. We're going to take 2 minus lambda times the determinant of its submatrix. So cross off the row in the column, and you should get 1 minus lambda 1, 6, negative lambda. So if I were to work this out, the first 2 terms go away, so you're left with 2 minus lambda times. If I find the determinant of this 2x2 matrix, you will get negative lambda times 1 minus lambda, minus 6 times 1 is 6. All right. This will give us 2 minus lambda times, if I multiply the negative lambda through, you'll get negative lambda plus lambda squared minus 6. If I were to reorder this, it looks like inside the bracket, you're going to get lambda squared minus lambda, minus 6. And remember, now that I've kind of cleaned this up a little bit, you're going to end up setting this equal to 0. So now the factoring takes over. The 2 minus lambda is already out here by itself, so I'm not going to mess with that. Instead, I just want to factor what's inside the bracket. So if you were to factor lambda squared minus lambda minus 6, you should get lambda minus 3 times lambda plus 2, and all of that is equal to 0. set all of your factors equal to 0. So 2 minus lambda is 0, lambda minus 3 is 0, and lambda plus 2 is 0. Solving each of these, you will find 3 eigenvalues of this 3 by 3 matrix. It looks like you're going to get lambda equals 2. The next one, if you move the 3 over, you'll get lambda equals 3. And on the next one, if you move the 2 over, you actually get lambda equals negative 2. And so in this case, this 3 by 3 matrix gives us 3 unique eigenvalues of the matrix. Now, you notice that I did not make you find the eigenvectors here. Now, we could plug each of those lambdas into our A minus lambda I, set up a homogeneous matrix equation, and go from there. But as you can probably already tell, that's very, very, very time consuming. All right. It also comes to the fact, especially when I'm giving assessments on this, that if you mess up finding lambda, there's no way you're going to get the eigenvectors correct because you're plugging the wrong numbers in. So what I will typically do is I will give you a problem like this where I make you find just the eigenvalues, and that will be one particular problem. Then what I will do is something like this. And we're going to do 2 of these together. Instead of making you find the eigenvalues and then find all of the eigenvectors, instead what I will do is I will give you a matrix. So as you can see, I've given you a 3 by 3 matrix here. And I'm going to give you one of the eigenvalues. In this case, I picked lambda equals 3. What I would like to do is I want you to find a basis for the eigenspace. Now remember, the eigenspace is every single eigenvector that exists. There's infinitely many of those. Back at the end of chapter 2, we talked about a basis. A basis is just a set of the eigenspace, or back then it was a set of the subspace. I'll remind you when we get to that part of how you take an eigenspace and put it into a basis form. We'll do that at the very end. So since I want you to work with lambda equals 3, and I want you to find the eigenspace of this, remember, this is asking us to set up a homogeneous matrix equation based on the lambda I've provided. So since the minus lambda, we know from the last problem, is it's going to go on the main diagonal, what I want to do is I want to plug lambda equals 3 into those quote unquote lambdas and create the A minus lambda I matrix. When I do that, so if I plug in 3 to all those lambdas, you will get 1, 0, negative 1, 3, negative 3, 3, and then 2, negative 2, 5. I'm sorry, 2, negative 2, 2. To make it a homogeneous matrix equation, I am going to add the 0 column onto the end. All right. So we need to put this into reduced echelon form in order to solve for the eigenspace. So to do that, first thing I actually notice is that row 2 and row 3 are multiples of each other, because the second row has a bunch of 3s, the third row has a bunch of 2s, and they have the same signs. Since all of those match, I know they have to be multiples of each other. So I know immediately that I can take the top row, leave it alone. I'm going to take the bottom row and make it all zeros. And then while I'm here, I'm going to go ahead and take row 2, and I'm going to multiply everything by a third just to make the arithmetic a little bit easier. So that would be 1, negative 1, 1, 0. All right, so now I need to get rid of that second 1 in the first column. So I'm going to take row 2 and just subtract the number right above it. That will give me 0, negative 1, 1 minus a negative 1 is 2, 0, and then 0, 0, 0, 0. So we're almost in reduced echelon form. The only thing is that our second pivot position needs to be a positive 1. So I will now take row 2 and multiply it by a negative. So we get 1, 0, negative 1, 0, 0, 1, negative 2, 0, and then the third row is all zeros. Writing out what this means that x1 minus x3 must be 0, x2 minus 2x3 must be 0, and thus x3 must be a free variable. Solving for your basic variables here, you will get that x1 is equal to x3, x2 is equal to 2x3, with x3 still being free. Now, going back to the first problem we did with eigenvectors, we wrote this in parametric vector form. So we would write that vector x is equal to your free variable x3, and then you got to find the coefficients here. So let's see, using your coefficients, that would be 1, 2, and then 1 since it matches the free variable. And this right here would generate every vector in the eigenspace. Because remember, there are infinitely many of them, keeping in mind that we cannot let x3 be 0. Our question is asking for the basis. So it's asking for a linearly independent set based on the eigenspace. Now, the easiest way to do that, and I'll put it down here in parentheses, is let x3 be a value. That's the fastest way to find a basis. Remember that bases have to go inside braces, and then just let x3 be whatever number you want it to be. So to make it really easy, I'm going to let x3 just equal 1. Because if I let x3 be 1 here, that's not going to change the vector that's attached to it. So I could simply just write the vector down 1, 2, 1, and that would be a basis of the eigenspace. Just out loud, another example, why don't you let x3 be 2? If you let x3 be 2 and multiply it through, you will get 2, 4, 2. That is also a basis of the eigenspace. Somebody usually asks me, why do you not do multiple vectors? Why is it just 1? Well, keep in mind, if you let x3 be a couple of different numbers, all you're doing is creating multiples of each other, which those are not going to be linearly independent, so that can't be a basis. So however many vectors you get, you just let each of those be a free variable, and that creates your basis of the eigenspace. Very good. Let's do a second one. All right. So I created a new matrix for you this time. It's still 3 by 3, and we're going to let the lambda for this problem be 2. What would be a basis of the eigenspace for this particular problem? So remember, in your mind, you know that we're going to have a minus lambda down the main diagonal. And we're going to take the lambda equals 2, and we're going to substitute that in to start to create the homogeneous matrix equation. So over here on the left, if I plug in 2 down the main diagonal, you will get 2, negative 1, 6, 2, negative 1, 6, and then 2, negative 1, you guessed it, 6. I have a method to my madness. You'll see in a second. To make this a homogeneous equation, I'm going to put zeros down the last column, which doesn't really mean much, but we'll use it there. As you can obviously see, based on the numbers I cleverly picked, all 3 rows are multiples of each other. They're actually exactly the same. So when you have more than one row that's a multiple, which we don't see very often, you just need to leave the topmost row alone, and every other multiple of that row becomes all zeros. So you're going to actually end up with 2 rows of all zeros. Now, I need to go ahead and scale the top row to get it into reduced echelon form. So I'm going to take row 1 and multiply everything by a half. So that's going to end up giving me 1, negative 1/2, 3, 0, and then we'll fill in the rest of the zeros here. Creating your basic variable equations becomes the following. You will have that x1 minus half of x2 plus 3x3 needs to equal 0. And since there's no pivot positions in the x2 or x3 column, I know that x2 and x3 are going to be free variables. Solve for your one basic variable, which is x1, and we will get x1 is equal to half of x2. Oop, that's an ugly 2. Let's try that again. Minus 3x3 with x2 and x3 still being free. So as far as the eigenspace goes by itself, we can write vector x as x2 times a particular vector plus x3 times a different vector. So putting in your coefficients here for x2, you're going to get 1/2, 1, 0. And for x3, you should get -3, 0, 1. So that is your eigenspace. But we just want a basis of the eigenspace. Now, the good news is that since you've got two free variables, each of those free variables is attached to a vector that would be linearly independent of each other. If you think back to when we first defined homogeneous equations and all that stuff in chapter 1, these two vectors have to be linearly independent of each other, assuming that x2 and x3 both are not 0. Because if they're both 0, you're undoing the whole point of this. So if that's the case, we need to create a vector that has to do with x2, and we're going to create a different vector that's attached to x3. So you can let x2 and x3 be any coefficients you want besides 0, and we'll create them. Just to be different, and once again, you can always just do one, but I want to be different so you can see counterexamples in the lecture. What I'm going to do is I'm going to let x2 be 2. And if I were to plug x2 equals 2 in and distribute that to all three elements, 2 times 1/2 is 1, 2 times 1 is 2, and 2 times 0 is 0. That would be an eigenvector of the first one. Likewise, I'm going to let, just to be different, let me go back to blue. I'm going to let x3 equal -1. And I'm going to plug that right here and multiply -1 by all three elements of that vector, which would be +3, 0, -1. Like I said, since I knew, as long as I did not let x2 and x3 be 0, which we're not allowed to do in this section, I knew that these two vectors were going to be linearly independent of each other. And you can double check that by one of our shortcuts. Those two vectors are not multiples of each other. So for your basis, this is the basis of your eigenspace. So if you're thinking of, okay, I'm starting to kind of see a pattern here. The number of vectors in a basis should equal the number of free variables. If you go back to the previous problem that we did, we only found one free variable with this lambda. So we only had one vector in our basis. In this one, since we had two free variables, there ended up being two vectors in our basis. And that's true for every problem that you'll do when you have to find basis of eigenspaces. All right, and to kind of wrap this section up a little bit, there's only one other type of eigenvalue that you might run into. If you ever run into an upper or lower triangular matrix, and either one is true, then the eigenvalues of that matrix are simply just the entries on its main diagonal. Now, just to be different, I created a lower triangular matrix just because we see upper triangulars so much more. Now, while we won't see a lot of lower triangular matrices in this class, it still holds the same fact. Since this has zeros above the main diagonal completely, by definition, the eigenvalues of A must be the entries on the main diagonal. So what you'll notice is that we have lambda equals 4 twice, and we have lambda equals 1. I emphasize the word twice because we have not seen that yet today, where an eigenvalue can repeat itself twice. Interesting. We're going to get more in the next section into what that means, but a word that you will hear in the 5.3 video a few times is that when an eigenvalue, sorry, let me rephrase that, when an eigenvalue repeats itself, and it can repeat itself more than once, it can repeat itself more than twice. This is what a word you will hear called multiplicity. And multiplicity is a word that applies to the repetition of eigenvalues in linear algebra. Like I said, we'll talk a lot more about this in the next video for section 5.3, but I don't want that to be a word you haven't heard before as you walk into the next video. All right, and last but not least, not a problem, but just a couple of definitions that are going to lead into the next video. So I'm going to go through this and I'm going to kind of foreshadow what we're going to see in the next video, which is one of the biggest topics we cover. So we're going to bring back the invertible matrix theorem. And I wrote continued again, trying to be funny, because I feel like we keep bringing this theorem up. If you remember, the whole point of the invertible matrix theorem is that if A is an n by n matrix, then every statement in that theorem is either all true or they are all false. With the big statement being A is an invertible matrix. Well, the two new things that we have learned here in the last couple of videos that we can add on would be part R and part S. And actually, if you look at them, part S is the one we talked about in the last video that says, if the determinant of A is not equal to 0. That was part of our chapter 3 discussion. If the determinant of a matrix is not 0, then A must be invertible. We already talked about that a little bit. The new one that we're adding is part R. The number 0 is not an eigenvalue of A. So if A is invertible, 0 cannot be an eigenvalue. So what that's going to tell us in the next few sections is that if we are working a problem and we find the determinant and find the eigenvalues of A minus lambda I, if 0 comes out to be an eigenvalue, immediately we know that the original matrix A is not invertible and thus cannot be used for certain things. Keep those two in mind as you're studying and you're reviewing the videos. That will show up again in a little bit in the next video or two. The last thing I want to do is I want to throw in a little bit of a theorem that kind of helps us out. And we've kind of already mentioned this, but I wanted to actually give y'all the theorem that states what I mentioned earlier. So if V1, V2, and VR are eigenvectors that correspond to distinct eigenvalues, all right? So let's say that you have found a bunch of eigenvalues of a matrix, and for each of those eigenvalues, you have found eigenvectors. The good news is that every single eigenvector that comes from a different lambda are going to already be linearly independent of each other. So kind of, for example, if your two eigenvalues were lambda 1 equals 1 and lambda equals 2, if you were to find an eigenvector of both of these, I can guarantee that those two eigenvectors are going to be linearly independent of each other. Not only that, kind of going back up from my discussion earlier, let's say that lambda equals 1 actually gives us a basis of 2 eigenvectors, while lambda equals 2 would only give you a basis of 1. Like I've already told you, these two vectors have to be linearly independent of each other based on the idea of an eigenspace and of a basis. What we're also claiming is that this V3, whatever this third eigenvector is in your basis, it is linearly independent to not only V1, but also V2. So all that to be said is that if you use multiple eigenvalues, no matter how many eigenvectors you find for each and put them all together, if you create a basis accordingly, you will find a linearly independent set of eigenvectors, which is very important for a big star here. This is a huge idea that we are going to see in the next section, in section 5.3. So before I let y'all go at the end of this video, so I'm done with introducing eigenvalues and eigenvectors and eigenspaces. What we are going to lead into in the next video, and I'll go ahead and give you a heads up, it is one of the longer videos in this class. There's a couple of huge ideas we have to go over. In 5.3, we're going to go over the idea of diagonalization. We're going to learn the first of two different ways that we can factor matrices in this class. So that does not work the same as a quadratic that we saw today. Factoring matrices is a little bit more difficult, but we're going to go over all of that in the next video.